By introducing the meeting. So today's speaker is Erik Ylipää from RISE. He's an expert in deep learning and sequence models, set function models, transformers. So please, Erik.
So thank you very much, Olof. And as Olof said, I work a lot with deep learning, and in particular for mathematical sets and sequences. So today I will talk about what I call unsquared transformers. So it will be a focus on transformers, and I'll try to give you all a pretty intuitive view on these new ways of trying to make these transformers more efficient. So that's the focus of today's talk. So an outline of what I will talk about. First, just a couple of examples of where we are seeing the transformer architecture being used. So I'll spend some time on this outline and wait for more people to arrive, I think. We're already quite a lot of people. So a lot of the talk will actually be about the transformer architecture. So I'm not assuming that those of you who listen to this know the architecture in detail. If you do, a lot of this will be all news. But if you don't, I hope you get an intuitive understanding of the issues with the architecture and also the kind of solutions we're looking at. So in particular, I will look at two different efficient transformer architectures. One is called Big Bird and the other is called the Performer. So Big Bird being in the line of Sesame Street characters started by Elmo and Bert. And at the end, I will show you some comparisons of a lot of different efficient transformers. But I highlight these two examples because I think they are the most interesting, at least for me. So just, I assume most of you have already seen one of the most, let's say, publicized applications of transformers used for language modeling and for creating these very powerful language models. So this is an example of text generated from GPT-3. I found this example very impressive. So as most of you probably know, it has been shown that, of course, this model have spectacular failure modes as well. So it's not really at the level of what some people might have kind of interpreted it as being, but still. So this text on the right hand side here is generated by only prompting the model with the title and the name of the author, and the rest of the paper is or this document is generated by this model, and it's able to hold a pretty cohesive narrative throughout regarding Twitter, and it's also quite humorous. So most of you are familiar with this, but we're seeing the transformer starting to be used in a lot of different applications, because the transformer, before that, yes. So an important point in this, and especially in regards to GPT-3, is that we're seeing an explosion in the number of parameters used in these models, the size of these models. So here, the question of efficiency is very important. So right now, this is mostly about the scaling of numbers of parameters, and that's not exactly what I will talk about, but it is definitely an important point. And being able to do these this kind of efficient transformers, as I'll show you, will also open the way for using the parameters more efficiently. But another interesting example of using the transformer is this image GPT. So we've seen recently a lot of transformers being used for images. This was from OpenAI using the almost exact same model as they used for their second generation of the generative pre-trained transformer, where they treat an image like a sequence. So they convert the pixels of the image to words using vector quantization to a fixed vocabulary of 50,000. Then they flatten those pixels into a sequence and use the GPT training on this. So just like language modeling. They also try the BERT masked language modeling objective. And what you can see on the right-hand side here is this model filling in obscured parts of images. So on the left-hand side, we have an image which has parts of it obscured, and on the rightmost columns, we see the original image. While on the columns in between, we see different generations by this model on images. And the kind of contextual knowledge it learns from just looking at pixels is amazing, I think. So the way it can actually fill in these architectural landscape, for example. So that's one example of how we're starting to see transformers being used in the very, very common domain of images in deep learning. But a very important application, one which I am involved in, is using transformers for graphs and for mathematical sets. So graph is a mathematical set, and we see that transformers are actually starting to give very good results in the domain of, for example, molecular property prediction. So this is an example of a paper where they enhance the transformer with path features, essentially looking at shortest path between nodes in the attention mechanism of the transformer. But the scores they achieve are quite remarkable. So we're starting to see this model being very useful for these kind of small graphs, which we typically use in molecular property prediction. We're also seeing them being used for more broader chemistry target. In this case, it's predicting the product from a chemical reaction. So using very straightforward language modeling techniques, encoding a reaction. In this case, you see that the thing here. This is a reaction encoded in a particular line format where the graphs have been linearized into string representations. And then you feed these string representations through a regular sequence-to-sequence transformer. And what they show in this paper is that they achieve very good results without using what's typically called template-based methods, where you try to match a reaction to certain templates to be able to predict the result. And this is a very important application for chemistry, in particular being able to go the other way around, which they have also, the same group, have recently done more work in that retrosynthesis. So we're seeing the transformer being applied to a lot of different applications. And in particular, I think graphs and small graphs is something where they really excel, which is what we have in chemistry, often in organic chemistry. So to give you a bit more background, I will explain the transformer architecture, and I will focus on the what we could call the transform layer, and in particular the heart of the transformer, the self-attention mechanism, which is also the issue with the transformer when it comes to computational and space complexity. When I do this, I will gloss over many details. So this talk is more about intuitions than it's about rigor, I would say. And in particular, when it comes to the architecture, I will not mention the residual connections or normalization layers and dense layers, which are all important parts of the architecture. But for now, we'll focus on the stuff which affects the complexity of the model mostly. So often transformers are portrayed as sequence models. I like to kind of go away from that. So a different way of looking at transformers is more of it's a memory model, where we have a dynamic memory and we have a mechanism which operates on this memory. So it reads from the memory and updates memory. And the way we do this for working with our inputs is that we initialize the memory with our input set. So for example, a sequence. And this means that we need as many memory slots as the number of elements in our input. But the neat thing about the transformer is that the number of memory slots we use is kind of dynamic. And it's really this read operation which we train, or read and transform operation. So first of all, imagine we have some kind of memory and we have an input sequence we would like to do something with. So what we do with the transformer then is that we take the sequence, we create embeddings from it. So if we think of this as a set and not a sequence, we need to somehow encode the order of the elements of this set. Typically we do this in transformers. There are many ways of doing this, but one popular way is to actually learn this, what's called positional embedding. So each element of this set has one part which is kind of the content, in this case, the word piece embedding, but also its order in the sequence, since this is now a set model. So this is how we typically initialize the model, and then we have this kind of mechanism which update the memory. So this is a transformer layer. And it consists of, simplified here, a read function and a transformation function. So this transformation function, that's typically a couple of dense neural network layers. So typically one hidden layer using a ReLU activation function. But the read function, that's where the heart of the transformer really is. So that's where we'll find this attention mechanism. And the way this works is that we apply the same, we can think of it as this read and transform function. We apply the same thing for each of the memory slots we want to update. So at each memory slot to update it, we read from the previous memory state. So that we have this kind of parallel update mechanism. And this is really the strength of the transformer in comparison to previously used models for sequences in particular, so RNNs. That this kind of update was sequential. So they had a sequential bottleneck, but in transformers, this is parallel. But I will focus on this read function in this talk. And then we can think of the transformer as repeating this process a number of times. So each step that you see here is one layer essentially. So we start with some initial memory, typically initialized with our input set. Then we have this learned function which we apply for each memory slot to update them. And then we repeat this process for as many layers as we have in the transformer. So this is a different way of looking at the transformer, and it actually has connections to a previous model called the differentiable neural computers. So there are actually close similarities between these two architectures. So this is more of a tangent. I'm not going to dive too deep into this, but essentially, if we simplify a differentiable neural computer in a number of ways, we end up with something which is very similar to the transformer architecture. That we have this memory, we have these read operations, we have this, in this case, the controller is the thing in the differentiable neural computer which transforms the things we have read out. And in this case, this would correspond to this transformation function in the yellow box I showed you earlier. But there are a number of differences which makes the transformer actually simpler, and I would argue easier to use. I won't dive too much into detail here, but if someone's interested, this is something I'd like to talk more about. But then we're going to focus on the read function, as I said. And the read function uses a mechanism called attention. We can also think of this attention as a read mask. So from our memory at the previous state, all of the memory slots, so to say, we want to read them differently, perhaps, or we want to have a mechanism which can select which memory slots to read, and that's what attention does. So essentially, we do this by creating this weighted sum of the memory slots, and these attention scores determine how much of each of the memory slots dominates the sum. So, for example, these are supposed to correspond to scalar values, and I depicted it like this to kind of highlight that you can think of this as a histogram. So these, all of these A1, A2, A3, A4, and A5, they are scalars, but they sum up to 1, and they are positive. So at the end, what we actually do here is that the read value from memory, the memory we read from, the value we read from memory, this Z. So this value, which will then be transformed before we update the first memory slot with that value. That is composed by this weighted sum, this weighted average of the memory. So we can see that when updating the slot, we actually read from all of the other memory slots. So this means that this operation will then be proportional to the number of memory slots we have. And the number of memory slots we have needs to be at least as long as the length of the sequence. And that really cuts to the heart of this issue. So just to show you kind of the intuition here is that we apply this for each of the memory slots we want to update. And again, we have as many memory slots as we have, at least as many memory slots as the input size. So this means that we do these operations also as many times as we have memory. So you can see here that we kind of get this quadratic behavior here. And to kind of summarize this in more compact notation, we implement this using matrix multiplications. So these different Z1s, all of these the values we read from memories are these weighted sums of the previous memory. And we can write it compactly like this. So A1 here is then the column vector for how to weigh the previous memory slots when updating memory position 1 and so on. By the way, Olof, if there are any questions in the chat, or if anyone has questions, feel free to interrupt me at any time. So just to show you kind of another depiction of this, and this is kind of the picture I will use to explain the issues and how we can try to solve them. So we can think of these masks I showed you previously, these histograms. Those are rows in this attention matrix. Then we multiply this matrix by our memory to get our new the values we read from memory. And in particular, the size of this matrix will be quadratic with the input length. So in this case, I use n. So as we increase the memory, or rather we increase the memory to be at least as many memory slots as the sequence input, then we also need to increase this attention mask. So this is where before we dive into the complexity, I'll just briefly mention the main idea behind attention. So these masks are particular in that they are dynamic. So we calculate the values of these masks based on the input. So, or if we think of the memory model, the mask to update a new memory slot should depend on the current memory state, so that we aggregate the memory slot differently depending on what state they are in. This is really the point of these attention mechanisms, is to compute these scores. And in the transformer, we use a mechanism called self-attention. So this is a pretty busy plot here. I'll try to break it down, so we'll spend a bit more time here. So first of all, it's a mechanism to determine how we read memory. And if we see this, by the way, can you see my pointer?
Yes, we see your pointer. And great. I follow the chat, so I will forward questions to you.
Thank you. So we can think of each row in this mask as corresponding to how will we read the memory when we update the corresponding memory slot. So for example, when we update the memory slot 1, how will we read the memory? And then we multiply this row by this matrix. So if there's a high value here, for example, that means that the last row here will also dominate this sum. If the values are more spread out, it will be more of a closer to the arithmetic mean of the memory. And what we typically see in attention is that this will have high values in a couple of places and low values typically in many places, because we kind of learn this more selective mechanism. So each memory read typically only attends to a few of the inputs, but we still need to compute all of these scores for all of the slots, because we don't know beforehand. And the way we do this in the self-attention mechanism of the transformer is that we have these contextual, or what should I call it? So when updating memory slot 1, I use a mechanism where a kind of content-based addressing. So the current state of memory position 1 is used to determine which of the other memory positions to include. And this is the origin of what we call self-attention. But for this to not, if I only used the dot product between memory slot 1 and the other memory slots, I would just have a diagonal matrix, or rather, we would always have most attention on the diagonals. So what we do before we take this dot product is that we actually create these linear maps of the memory positions. So xi here, this would be a memory slot. So x1, for example, is the first memory slot. But then we create what we call the query. So when I want to update memory position 1, I use the query vector, the current content on that memory position, transformed by this matrix WQ. And then for each of the other memory slots, I consider them as keys when I do this content-based addressing. So I do the same there. I have a different matrix, WK, which I multiply with each of the memory slots. So you can see that the first element here will be the dot product of the query key for memory slot 1 and the the query vector for memory slot 1 and the key vector for memory slot 1. And then to determine how much of the fifth value I would use when updating slot 1, I use the query for slot 1 and the key for slot 5. So this gives me then these scores, which I will use in the tension. And then we use the softmax function, which is exponentiating this dot product. And this is really the something which we will spend quite some time to discuss further. So breaking this down a bit more, this might look a bit complicated. This is a slide we will also look at again when we talk about the performer. But essentially, we can think of the attention matrix as being produced by these, we have these normalization factors. They are the ones which make sure that each of the rows here, that they sum to 1. And then we perform this dot product between the queries and the keys, and we can do this efficiently with a matrix multiplication. So this is a reason for why the performer typically works quite well, because this general matrix multiplication is very well optimized in most software. And then think of this exponentiation function. It's here it's element-wise, so it will act on each element in this in the resulting matrix here. And the resulting matrix here, it will be the number of memory slots times the number of memory slots. It will be the same size, of course, as this one. So we can write the whole, or think of the whole operation we do as we first create this attention matrix, and then we multiply that with our memory. So each row here is actually a vector. And then this Q and K, that's just from the previous slide, you saw that we did this like vector-wise for the memory, but we can do that just as matrix multiplication to get these whole matrices K and Q. And the main issue here is that what we have here then is an L by L matrix. Our memory is L by D. And now this notation is a bit confusing. They use L for the number of inputs in our sequence, while I used M previously. But still, so L will the number of elements in this L will of course grow quadratical with the size of the input. So what we end up is with this complexity of being quadratic in the input, and then also times D here. But D is a constant which we decide on. So it's essentially our representational capacity of the model, and we can choose to have that as high or low as we'd like to. And this is really the main issue with the transformer, that we have this complexity in the input size, which means that the input lengths we can actually work with, especially when it comes to memory constraint, is very low. So we've typically seen these kind of models used for language, for example, to constrain themselves to input sequences of, for example, 512, or at most a couple of thousand if you can distribute your model over many compute nodes. But it's a very limiting factor, of course. And what we'll talk about here is different ways of reducing this computational complexity. So this is a good survey of efficient transformers, which I can recommend. But they have this depiction of different kinds of attempts to do this. And we'll look at Big Bird first, which they classify as a memory or fixed factorized random patterns, because Big Bird uses a lot of different ways of doing this. But I will focus mostly on this fixed factorized random patterns. And then we have the low rank methods, which tries to solve this problem differently, where Perform is one of the most recent works. So one way of trying to attack this problem is to actually constrain this self-attention. So instead of producing this full matrix, which we saw before, we can say that, okay, we decide on a fixed neighborhood. So you see this block sparse, block diagonal matrix, where now each memory position, when we read, for example, memory position 2 here, we will only consider the 2 neighboring memory positions, which means that if this memory is initialized with a sequence, in the first layer, we will only be able to get information of the very close neighborhood. So typically, this example is, of course, very simplified. We typically have much larger neighborhoods than just 3 elements, but it will still, it's still a limitation. But this essentially limits the computational complexity then to the size of these neighborhoods instead of being quadratic in the whole memory. It's kind of only quadratic in this neighborhood, and then the number of neighborhoods increases linearly. So the sparse way, or different ways of trying to make this attention matrix sparse, is a very, very common thread. But then again, most of those methods, they make assumptions on the dependencies between inputs. So you assume that most of the information is local, or it has to be, for example, in this case, it has to be very local. Other examples use kind of randomly sparse matrices. So you get these kind of, you can think of it as shortcuts in the attention. So that with a couple of layers, you will be able to propagate information efficiently. But those are typically very hard to implement efficiently when it comes to the actual computation you need to do. So,
just a
yes.
quick question.
Yes.
Going back to the previous slide, is this something like a kernel method, meaning that you look over a full attention matrix, or is it just looking at the diagonal?
So in this example, this is just looking at diagonal or some fixed, or we have a sparse pattern which is produced somehow. It can be produced without being fixed, but it's not produced by kernel in this case. There are methods which does this, but the first example I will show you does not do this, while the second is instead a kernel method. So
okay.
There are, of course, a lot of different attempts to try to get around this quadratic complexity. But firstly, I'll talk a bit about Big Bird, because mostly because I kind of like the idea. And the reason for why I chose to explain the transformer to you as a memory model is really because it makes explaining Big Bird a bit easier. So as I said before, when we initialize this dynamic memory, we need to have at least as many memory slots as we have elements in our input set. But we can actually just add more memory slots. There's nothing really stopping us from doing that. So what they do in these kind of models, and Big Bird is not the only paper which did this, the memory transformer, sorry, I forgot the name of it. But there was a parallel work where they do almost the exact same thing. But the idea is then that we add a fixed number of memory slots. So this will not depend then on the input size. And then we have a peculiar pattern between how these memory slots and our input memory slots interact. So what we do is that, so the fixed memory slots, they attend to everything. So when we update the fixed memory slots, they have full attention in a sense. So they can summarize the whole sequence if they need to. But the neat thing is that we then use this restricted attention for our input slots to only work on, for example, a local neighborhood. That's one of the patterns they use in the paper, but also attending fully to the fixed memory. But since the memory is fixed, it's constant. So the complexity of this model is actually still linear with the number of input memory slots. This leads to a sparsity pattern for the transformer, which looks like something like this. So we have this fixed memory, which we initialize to some value. We can learn what value that should be if we like to, but the easy thing is to start with zeros. And then we have our input memory. And then we construct our computation so that it produces this kind of attention matrix. So you can think of the this restricted attention as kind of a windowed attention. But then we have this full attention between the inputs and the fixed memory, and the fixed memory attends from everything. So in this way, the patterns or the interactions, so to say, with elements which are close together in a sequence, for example, can be captured by these local attentions. But we still have these kind of information pathways going through this fixed memory back into our kind of sequence memory. And this way, we're not the problem with restricted self-attention without these shortcuts would be that it's difficult for information to flow, for example, from one memory slot to another, or to learn dependencies between distant memory slots, especially if the number of layers you have in the model is lower than the input sequence, which it typically is.
Erik?
Yes.
Would you say that this adds some sort of a bottleneck effect? And
yes.
Did they investigate this in any way?
No, or not that I can recall. No. Okay. It does introduce a bottleneck effect. And did I include that? No. One of the issues is that, of course, depending on what kind of interactions you want to capture and how much of the, so to say, dependencies are actually long range, you will need to increase the fixed memory size. So one of our colleagues, Amaro, he did also some parallel work to this, doing almost the same thing, and he experimented quite a lot with the size of the memory and had to use quite large memories to be able to get good performance. So that the size of the memory starts to almost be the size of your input sequences, and then you don't gain anything. And we'll see later on when we compare the different methods that actually the Big Bird, for a lot of the problems, it doesn't perform much better than the regular transformer. So mostly I think this is a really neat idea. And in particular, let's see, did I have a slide? No, I don't have a slide about it, but this is a really neat idea for graph convolutional neural networks or graph attention networks, where we typically have some kind of sparse structure induced by the graph structure, some sparse attention structure. And those networks are very limited because of this, the routing of information, that it's hard to learn global properties for graphs when you only have these local neighborhoods where you aggregate information. But adding these kind of shortcuts, especially with this, if we think of the transformer not as a, we have a sequence and producing elements of the sequence, but rather that we have a memory which we initialize with the sequence, but then it does kind of whatever it wants to with the memory. Then it's easier to kind of think of this just adding more memory slots to be able to get these shortcuts from anywhere.
Erik?
Yes.
You had a question earlier in the chat about how to encode the graph in the case of...
Oh, sorry.
So the question was, how do you encode the graph when working with the transformer?
That's a very good question. So I think I have some time to, I'll deviate a bit because that is interesting. So typically what you do I have a good slide to now? Not really. What you do is that if we think of our graph as our, let's V for the edge, for the node set, and E for the edge set. What we do with graph transformer is typically that we use the nodes of V as the inputs. So think of these as, we initialize our memory with a vector representation of each element node in the graph. Then we use the structure from E here to constrain the attention mechanism. So for example, if I write IAJ, would be some kind of function on the, let's say, VI, VJ, so that would be the node information. Then plus some function, for example, for some kind of, depending on the edge representation, perhaps this would just, this function would perhaps be just a constant if we don't have complicated edge information, but it could be more complicated. So E then would be our edge vector for I and J. So in a lot of cases, what it actually might do is that it might constrain us to only consider I and j, which are actually pairs of the edge set, so that we artificially kind of create this sparse graph imagine this graph corresponding to the adjacency matrix of the graph. And then we just aggregate information based on that, and then perhaps we don't have this. But we could as well have some kind of function which operates if the edges are, for example, labeled or they have features. So, for example, in a molecular structure graph, the edges typically correspond to bonds, and bonds can be different. So you typically want to include the bond information in that graph. So that's kind of a schematic way of how you encode this, that you actually, in the attention mechanism, you explicitly introduce things for the handling the graph structure. And that's one way of doing it, but a different way, which I'm partial to, which people there isn't much work on it, is instead that So we have our node set, we have our edge set. So instead, use the edge set as the inputs to the transformer, and then let the transformer figure out how to combine edges in important ways. There are of course a lot of difficulties in how do you encode each of the edges, and I think there's work to do there. So I done some work doing this, and for some problem it works surprisingly well, just applying a regular transformer to the edge set of the graph. But one issue is really node labeling. Then becomes an important point. So how do you label nodes? So that's enough for a detour for now. So that could be a different talk perhaps. But then briefly about the performer. So this paper is quite recent, so September, and it's a really interesting contribution. So the paper is actually there's a lot of math in it. I will not go into the math. This will be more of a talking about the intuition behind what they do. So essentially, we on the left-hand side here we have the issue. Now the question is, would it be possible to actually factorize the matrix A here into two lower ranked matrices, these Q prime and K prime, so that we could reorder the computation and perform these K prime transpose times V before multiplying in Q, instead of first multiplying Q and Q transpose and Q prime K prime transpose. So this is really at the core of this paper. Other papers have done similar things here. The question is really how we do this, because A here is produced by this the softmax mechanism, or softmax on top of the Q times K matrices. So we can't just easily linearize this. But here's really where the idea of so this is perhaps a bit hand wavy, but the idea is that we can approximate this attention matrix using essentially a kernel ID. So what if each of the element in this matrix could be approximated by a kernel? So I think I didn't actually include but essentially we can think of a kernel as having two vectors, or wanting to learn some kind of scalar value between two vectors. And in this case, let's write Q and K. We might want to, in this case, have each of these elements should be represented by some feature function of Q and some other feature function. So phi here is a feature function of K. And the idea with kernel methods is typically, or the kernel trick, is that these phi, they might produce new features of these Q and K vectors, which are very, very high dimensional. So explicitly performing this inner product is prohibitive or even impossible. But we can actually construct functions which implicitly perform this dot product. Now the idea here is to actually explicitly perform it. So actually, if we find these feature functions, if we define them, we could perhaps approximate each element here using this dot product instead. So by doing that, suddenly you can see here, this Z is what we read from memory. Now, instead of having previously, we had X here like this, which meant that we couldn't really do this trick of multiplying this matrix with the memory before multiplying with this Q matrix. But now if we instead can pull this or approximate this this attention matrix using this inner product, this dot product, then suddenly that's something we can do. So now we can perform this multiplication beforehand. And that's really the key idea behind the Performer paper. So what they do, they spend a lot of time to actually finding this kernel, which is a good approximation for the softmax. And what they use is something called random features. And this, from what I understand, and this is really outside of my field, but it's closely connected to an idea of random Fourier features. So there was a lot of work in this on this in the early 2000s. So Benjamin Recht and I forgot his first name, but Ramini, they did something they called a random kitchen sink, I think. And this is closely related to that work, that we can actually, so this X and Y here, that would correspond to these, and SM is softmax. So this value I showed you before, this exponential. So I won't go into the details of the math here. But essentially by doing this kind of random sample of feature functions, we actually get a good approximation of this. They show that this is a good approximation, and the property is kind of what's the variance of this estimator. So we're trying to estimate the softmax values of the attention matrix, and they show that this estimator is unbiased. So with increasing number of these omegas we draw, we get better approximations of this softmax value. And in particular, we can see that this is actually corresponds to a thing we can decompose, like here. So I should say these phi's here, think of them as acting on the rows of this matrix, so that we create new matrices. I'm not going into much detail there. So this is kind of hand wavy, and I'll gloss over it. But one thing they do show with this is that so this is where they show the computational, the time it takes for this model to do a forward propagation. On the x-axis here, we have the length of the sequences, or the log2 of the length of the sequences. So we would actually have, this corresponds to a sequence of length 2 to the 18, 2 to the 10. So this would be 1024. Well, this would be a quarter of a million, roughly. And we see that, so opt here, this is the most simple attention mechanism we can think of, or at least one of them. So we have the Q matrix, or Q matrix, I should write. Q matrix, the K matrix, and the, in this case, I'll call it M because I call it that, our memory, which we want to aggregate. And the opt method just returns M. So it doesn't perform any kind of attention at all. So it's kind of the fastest way of producing a new memory, to just be the identity, return the previous memory state. So that's this black line with crosses. And we can see that the different batch sizes for the performer actually scales in the same rate as this identity method. While these dashed lines, those are regular transformers, which you see they start increasing at a different rate. So this is a log plot, and this rate would then correspond to increasing in a quadratic rate, while these ones increase linearly. And another thing that they show, so one really neat thing with this, that we can, this approximation of the softmax, we can actually drop in a pre-trained model. So, or we might already have a transformer, and we just replace its softmax. Now they show here, so this is on 1 billion word benchmark, and I think it's a language modeling benchmark. If someone a bit unsure about it, but anyway, what they show here is that by taking a checkpoint of a trained transformer on this. And these are really, think of these as comparing apples and oranges, because the transformer here starts learning from scratch, while they actually initialize the performer here. You see it's called fine tune with a high performing checkpoint of the transformer. But what they see is that by fine tuning this a bit with the new this kernel method, they're able to reach performance comparable to the transformer relatively early. So that's really neat that you can get this computational, this lower computational complexity, linear computational and space complexity for a pre-trained model. So finally, we will look at some comparisons. And this is from a study which is currently under review at iClear. Now it's also available on ArcSight, so the anonymity is kind of busted. But still, it's based on a benchmark, or they try to devise a suite of benchmarks, which is supposed to gauge the long-range capacity of this model. How good are they at modeling long-range dependencies? They have a set of tasks. One is called list ops, which is essentially you have a nested list or list of lists of lists, and for each list you perform some kind of reduction operation, like mean or sum or median. So think of it as kind of a Lisp program with only these simple reduction operators, and then the model is supposed to, for these very long lists, predict what the actual result is. Text, that's a sentence classification IMDb on the byte level. So actually having to learn how to decode, for example, a UTF-8 encoded file. Retrieval is document retrieval, where reading whole documents, you're supposed to predict whether they are similar or not by producing a single representation of those. And then image is image classification, but on the pixel sequence level. And then Pathfinder is kind of a task where, given an image, you're supposed to connect the dots and determine connect line segments, I would say, and then given dots on that segment, determine whether they are connected or not. So you can have a look for further details if you'd like to in the paper. But what we can see here is that when it comes to performance on these, there is the regular transformer. So they run this on good enough hardware that they can run a regular transformer with full attention, but it performs quite well. So, which is not surprising. So think of the transformer, it should perform well because it's allowed to essentially have unhindered attention over all pairs of sequences or tokens, while the other model somehow restricts that. And we can see that the Big Bird and Performer, while not being the highest performers here, are doing quite well. So for some problems they are doing worse, for others quite good. But I think the retrieval task is quite interesting in that we see the Big Bird is actually quite good at doing the retrieval task. Well, this path X, sorry, I don't remember the details for the X thing here.
So in this benchmark paper, do they include some runtime?
Yes, so that's the more interesting part, I think, when we talk about this. So the performance, we would like to be close to the transformer in performance, but what we really care about is runtime. So what you see here is they have steps per second, so this would correspond to kind of the how we scale with sequence lengths in time complexity, and then peak memory usage, which would correspond to space complexity. We can see for time complexity, so these 1K, 2K, 3K, 4K, that's the sequence lengths. So you see that 4K is 4 times the length of the first year, obviously. So what would like to have is kind of a linear decrease in number of steps per second. And we can see that the performer here is actually performing really good here. While for peak memory usage, we would like to see a linear increase in memory. And we see once again that performer is doing really well here. So this is really, I would argue, there are a lot of models here which are performing well, but for me, I think the performer is one of the most interesting of this architecture. And here they provide this plot which I think is a nice summary of the trade-offs between these different models, where we see a speed, so examples per second, where higher is better, of course, and this LRIA score, that's the average score on these tasks, where we see that the performer is at a pretty good point where it's the fastest and performs relatively well. Now, local attention is perhaps, the tasks are devised so that local attention should perform poorly. But then we see that by actually having the big bird's extra memory, you're able to get quite high performance. But then the problem is that how much extra memory do you need to add? And adding more memory means that, well, suddenly while you might be linear in length of the sequences, the memory you might need more memory if there's a lot of more memory slots, I would say. So sorry for confusing, space complexity. But these, as I said, these fixed memory slots which we add to the big bird, you might need to add a lot more than the sequence length, for example. So we can see that the big bird and transformer aren't really that far apart when it comes to speed. But so this is kind of a summary. I think what we're seeing right now is it's a fantastic progress in this area. So we're seeing a lot of models which reduce the quadratic complexity of the transformer to linear in both space and times with regards to input length. And in particular, the performer, I think, is really interesting here. This means that for just recently, so I showed you the image GPT, they worked on very small images, very low resolution images, because they, with increasing image resolution, we would then have kind of a to the power of 4 increase in computation times, is increasing the width of an image, maintaining the ratio, so to say, between width and height, will quadratically increase the number of pixels, which would then, mean that we're very limited in how large images we could actually work on. But another very interesting domain which the performer also looks at is encoding, for example, large molecules, so large graphs. So trying to, for example, do prediction on protein structures. So this is a very, very interesting area of research, very active also. But also going into actually looking at very much longer documents than just a couple of hundred, or at most 1,000 or a couple of thousand tokens. But the reason for actually focusing on Big Bird and Performer is that these memory issues we have with Big Bird, or rather these fixed memory slots we add, and the issue that we might need to add a lot of them, by complementing that with a Performer, I think there's a really interesting space of performance there. So actually being able to have a really large fixed memory in Big Bird, but still have a decent computational complexity. So that's really one of the areas I think will be really interesting going forwards, the coming couple of months. So the progress here is staggering. Most of the examples are from this year. All right, and with that, I'm happy to discuss or take any questions.
Thank you. So did you say what is the space complexity of the Performer?
So the space complexity of Performer is also linear. And one way we can see this is that if you see the space complexity increase here, you can see that you have, well, roughly linear increase with 4 times the sequence length, the peak memory usage. I mean, this is kind of an inexact measure, but you still see that it's not more than 4 times the memory usage for a sequence length of 1. While for the regular transformer, you see that it increases.
all of these are much better than the transformer.
All of them are.
Perhaps the synthesizer is the most limited one.
Yeah, the synthesizer is a bit weird in many cases. So I think they include it mostly as a because it got some attention. Where they, for a lot of the experiments they do, they kind of complement. They actually use the transformer attention, but they also have these, fixed learned attention matrices. So yes, I think I just picked two of these because I think they are interesting. And in particular, I think they will be interesting in conjunction. I think we will likely see a lot of new work on this, which might improve using similar ideas from these papers or other ideas. For a bit there. Can you still hear me?
Yes.
Yes, good. I heard a beep in my headphones.
Okay, do we have more questions?
Erik, I have a question.
Yes.
So in the performers, the reason why we want to basically decompose how you showed there is that we assume that this first matrix is dense, right? Because if it was sparse, most of zeros, it wouldn't be a problem. Is that correct? The A matrix.
So the problem is, that sparsification or that sparse matrix, it is often quite sparse, but it is that as a result of this attention mechanism. So had it been a fixed, and I think this is what they look at in the synthesizer, if you have a fixed sparsity there, so that you have a fixed attention mechanism, then the sparsity is much easier. But since the attention mechanism needs to be computed from the memory slot, so to say, you don't know beforehand the sparsity pattern. That is dynamic. That changes as soon as you change the one memory slot. The attention mask will also change.
But isn't it, if you look at this A matrix actually as this attention sort of graph, what you need that you have to have this graph of a short diameter so that information flows very quickly. That what you showed in a sense in a big bird just a few slides before.
Yes.
And they use this memory, the hubs. In a sense, they make hubs.
Yes.
In order to have this one hop or two hop in a sense flow.
Exactly.
But why not to just instead of these hubs make sure? I mean, there are many ways to do it to sparsify this graph in a way that you are assured that you have a very sparse yet very low diameter graph, and then this problem disappears of trying to decompose this nonlinear, what this performer did.
Well, if you have suggestions, I think this is a very fertile area of research.
I mean, to some extent, if this is really applicable to graphs, and I mean, if you go back a few slides where you showed this here, yeah. So basically, so what I understand, this is the problem of the initial A. Right, and at the moment it's just some kind of a graph of a long line, like a connected something like this, right? So what we want is to make as little as possible ones here, or let's say non-zero elements, so that we have a structure that assures low diameter overall.
Yes.
So,
exactly.
And I guess, I mean, there are plenty of ways to do it very easily. So I just know whether people looked at it.
Yes, and in particular, this random sparsity pattern has also been used and is used in Big Bird. I'm not including them here, mainly because I don't think they are too important when you have this. So you have a two-hop information flow here through the fixed memory. So I have a hard time seeing how the random pattern would help then. But in general, you could have random patterns, and people have done that, definitely.
I mean, random, we know that random is log n length, but you can do even better because you don't need to be random. You can just make, in a sense, like a hierarchical tree structure. And on top of, on that graph so that this information aggregates, or maybe even adaptively put zeros while training so that you arrive into the right, very sparse.
Yes. Typically, to adaptively do it, you typically have to actually perform the full computations.
So maybe the beginning is expensive, but then later will be cheap.
people have done that to try to train first and then see what sparse patterns do you get, and then try to sparsify. Kind of similar to pruning in neural nets. It's a bit more complicated with attention mechanisms, but that has been done. But preferably, we would like a mechanism which doesn't have to go that route. And these two mechanisms, in particular, the performer, does do that. So I think one issue with implementing the let's say you have these, as you pointed out, we can have these shortcuts. We try to have a few random points where we get a very low diameter, even though, or a lot of short route between any two memory slots. But still, the implementation of that is typically very non-trivial. So a regular transformer is very easy to implement. It's just a matrix multiplication. But as soon as you start to do this sparsely, then the implementation becomes, you need a custom implementation typically, and it's hard to make that efficient. So it kind of becomes a systems issue. And you will suffer more because it's difficult to implement, not really because theoretically, it would be a good idea.
We have another question in the chat. So the question is, are transformers a generalization of convolutional neural networks? If so, how would CNNs look with the notation used in this presentation?
So to say that are they a generalization? Yes, I think one could think of that. In a lot of ways, a transformer allows you to kind of efficiently model hierarchical compositions on sets. That sounds very hand wavy, and it is. But this attention mechanism essentially allows us to, for each step, select a few of the elements in the set to operate on. And then when we do this in steps, we can get the same kind of idea we have in convolutional neural networks, but we're no longer constrained to this locality assumption.
Can you encode the locality using the attention?
You can encode it, but the idea is that the network learns to encode it. So for example, for the image GPT, if locality is important, the attention mechanism can learn to actually leverage that. So that but still, I think one major limitation, at least before these works, is then that the computational complexity is much higher. And if you have any more questions, you can always send them through mail.
Thank you for the talk.
Thank you.
Thank you.
Bye, everyone.
Thank you. Bye-bye.
Thanks a lot.
Next week, we'll talk about federated learning, and Edwin Listosek is giving a talk. Same time next week. Bye-bye.
Bye-bye.